Hello everyone, and welcome to some remote learning. In today's video, we're going to go over the definitions of a secant line and a tangent line. That way you can better understand why we're learning how to take the limit and then how that applies to the derivative once we get into that. But for now, let's just go over what a secant line is. So how do you calculate it? A secant line is a line that intersects a curve or a function at least twice. So that means that we can use those 2 points to make that line. And what do we need to write a line? We need a point, at least one, and a slope. So we use those 2 points to create that slope and then use one of those 2 points to help us then create the line. Let's take a look at this below. Here I have some function. I don't have the equation for this function, I just have a set of points. So if I want to find the secant line that goes like so, that secant line is my line in blue. And you can see that it intersects the graph at the point 1, 1 and the point 2, 2. And it's a secant line because it's intersecting at those 2 separate points. And remember, in order to write an equation for a line, we need the point and a slope. So first let's talk about the slope. Remember, slope, back from just basic algebra, is rise over run, or the change in y over the change in x. So I can take either point at the start to find my slope. Let's go ahead and use the point 1, 1 as our starting value. So my change in y is going to be that y value, so my slope m, my y value of 1 minus my other y value of 2, and the x's happen to have those same exact values. I have an x value of 1 minus an x value of 2. So this is our change in y over our change in x. So those triangles represent delta, meaning change in y over change in x, that's our slope. So our slope m is 1 minus 2 gives us a negative 1, over 1 minus 2 gives us a negative 1. Negative 1 over negative 1 is a slope of 1. So knowing the slope, we can use our starting point of 1, 1 and calculate point slope form, and then we'll go ahead and either leave it like that or write it in terms of slope intercept form. It's up to you. So we have y minus y1 equals m times x minus x1. This is point slope form. Point slope form, we have a point, x1, y1, and our slope. So let's plug in our x1, y1 values, and that's going to be my 1, comma 1. So plugging in 1 for y and 1 for x. So I have y minus 1 equals m, which we also got to be a value of 1, times x minus 1. Here's point slope form. It's perfectly okay to leave this as such, but let's go ahead and rewrite it for practice in y-intercept form. So y-intercept form is where y equals mx plus some intercept of b. And if you can see this line here, it intersects at the point 0, 0. Let's confirm that. So we'll have y equal to x minus 1, and then I'll add 1 to both sides to get rid of the 1 that was with my y. So we get y equals, well, x minus 1 plus 1 is x. So we have our slope of 1 and our y-intercept of 0. So this secant line from the point 1, 1 to the point 2, 2 is y equals x. So again, the steps for finding a secant line are to find 2 points where the secant line intersects the function. Then, to make a line, we need a point and a slope. So with those 2 points, we can make a slope. But let's talk about how exactly to calculate a tangent line, because a tangent line is slightly different in the fact that it only intersects the curve at 1 point. So again, if we need a point and a slope to make an equation of a line, in order to get that slope, we need at least 2 points. But if we only have 1 point where that tangent line is intersecting our function, there's not really a way to calculate the slope. But let's fill in a table calculating secant lines that are getting closer and closer to roughly what that slope would be. So for example, what we're going to do up above is we already have this blue secant line. If I want to find the tangent line at the point 1, 1, the tangent line intersects just this point 1, 1 locally. Obviously, if we had some graph, I'll just do a quick sketch over here. If we had some equation or some function that looked like this, obviously when we go to find the tangent line here, when we try to draw that to where it only intersects at one point, we need to make sure it intersects only at one point locally. Later on, I don't care if it intersects again, but I'm more concerned about it only intersecting once locally. So in the neighborhood of that point. That's what a tangent line is. So if I want to find an equation for my tangent line at this point 1, 1, if I was to roughly draw that, you can kind of see how that yellow line touches the function just at that one point. Now notice that the slope of our secant line that we did, that blue line, is very different from the slope of that yellow line. But if I continued to make my secant line where my second point, the point that's not 1, 1, is closer and closer to 1 in the x, you can see how if I was to connect those 2 points, let's connect 1 and 1.5, then we'll connect 1.25 and 1, then we'll connect 1 and 1, you can see how it's slowly getting closer to that same exact slope. So we're going to make a table of values that slowly get closer to that x value of 1, that point where we want to figure out our tangent line, in order to get a rough estimate. So lucky enough for us, we already calculated when the x value was 2. Remember, when the x value was 2, f of x, our y value, was also 2. And 2 minus our function at 1, which is 1, over 2 minus 1, the x value minus 1, we got 1 over 1, which gave us 1. Or in our case, we had flipped those points around and got negative 1 over negative 1, which the negatives cancels out. So again, it doesn't matter what point we start at, as long as when we go to calculate the tangent line, we get closer to the x value at that point. So now let's look at an x value of 1.5. Well, if we look at the graph above, when we're at 1.5 in the x, we're at 1.75 in the y. So let's fill that in. Now, in order to calculate, we need to do 1.75 minus our function at 1, which when we're at the point 1, remember we are at 1, 1, so 1.75 minus 1 is going to give us 0.75, and that's going to be all over 1.5 minus 1, which gives us 0.5. So if we have 3/4 and we're dividing that by 1/2, that's going to be 1.5. So you see our slope changed from 1 to 1.5. Now what happens when we use the value of 1.25? Well, when we're at 1.25 in the x, we're at 1.4375 in the y. So f of 1.25 is equivalent to 1.4375. Now I'm going to round this just to make it a little bit easier, so I'm going to round it to 1.44. So 1.44 minus 1 gives us 0.44, and then we're dividing that by 1.25 minus 1, which is 0.25. Calculating this, 0.44 divided by 0.25 is going to give us 1.76. So our slope is even bigger. Now if we look at 1.1, which is even closer to our x value of 1, we're at 1.19 for f of 1.1. 1.19 minus 1 is going to be 0.19, and we're dividing that by 1.1 minus 1, which is 0.1. So 0.19 divided by 0.1 is going to be 1 0.9. So you can see our slope is getting closer and closer to some value. Now, it's a little hard to know exactly what value it's getting closer to with only these set of points. So the next step would be to get even closer to 1. So doing a number like 1.01 or 1.00001. You're getting closer and closer to 1. You're going to get a more and more accurate tangent line. But we can never just plug 1 into here because 1 minus 1 gives us 0. We're undefined. That's why we have to get closer and closer to that x value. Now what I've actually done is I've graphed this, and we're going to look at that table with the graph so that you can see how the secant line gets closer and closer to what the tangent line should be. So let's go ahead and pull that graph up now. So here is our same exact graph, just without the points labeled. I have my table here, and you can see that when we plug in 1, our slope is undefined. And my f of a is when a is equal to 1. I left this as a variable, and I'll share this link in the video description so that you guys are going to be able to play around with this function. If I wanted to find the tangent line at 2, I would set this a value to 2 and get closer and closer to x values of 2. However, I set my a as 1, so here is f of 1 minus 1, all calculated in my table for me. And you can see here were the values we got. We got 1, then 1.5, and then I rounded, so I got something close to 1.75, 1.19, we got 1.9, then let's do 1.01, that's 1.99, 1.001, you can see that's 1.999. We're getting closer and closer to what value for our slope. For this slope column, we're getting closer and closer to the value of 2. And if I actually display my secant function, if we start at 2, so right now I'm sliding this bar for n. N is representing my different x values getting closer and closer to a. That 1, you can see how my secant line changes and gets closer and closer to what my tangent line would be. So now that we know that our slope is approximately 2, let's actually figure out what the tangent line equation is. Because remember, in order to write an equation, we need a slope and a point. We've got the slope, we've got the point, let's use them. So our slope, m, we could see that those numbers were getting closer and closer to 2. So I'm going to use my point 1, 1, because that is the point that falls on the tangent line, the only point that intersects the function on that tangent line. So we're going to have y minus y1, which is 1, and that's going to equal our slope m of 2 times x minus x1, which is also 1. This is point slope form. We can go ahead and leave it as is, but let's go ahead and simplify down, writing this as slope intercept form. So just isolating my y. I'll get y equals 2x minus 2 plus 1. So y is going to equal 2x minus 1. That is my tangent line at the point 1, 1. And if you could envision extending that yellow line down, you would see that it would indeed eventually intersect at -1, that y-intercept. Now, if you notice from up above, we were changing x so that its values were getting closer and closer to the point 1. Closer and closer to that x value of the point we were trying to calculate the tangent line of. Essentially what we're doing here is taking the limit of the slope of that secant line as x gets closer and closer to 1, so as x approaches 1. And the wording of that might be a little confusing, so we're going to clarify the limit and show you how to calculate that in the next couple of example videos. But for now, let's do one more problem before we dive into actually figuring out what limits are and how to use them. So let's go ahead and use this in a real world application, like a physics application. If time is the independent variable, x or t, and position is that dependent variable on our graph, then the average velocity represents the slope of the secant line, and the instantaneous velocity, the velocity at that given point in time, represents the slope of the tangent line. And remember, velocity is distance over time. So another way to think about this would be speed, except speed is positive, so we would have to take the absolute value of that velocity we calculated. So in number 1, if we use the function f of x equals negative x minus 1 to the fourth plus 2 to answer the following below, we're going to first calculate that average velocity between the time of 1 second and the time of 2 seconds. Average velocity, slope of the secant line. So all we need to do is find slope. And in order to calculate slope, we need 2 points. We know we're going to use 1 for x and 2 for x. So we're going to need to calculate 1 f of 1, and then we're going to need to calculate 2 f of 2. In order to calculate f of 1, we're plugging 1 in for x. That's going to give us our y value, or our function value, at the point 1. Plugging in 1 is going to give us 0 plus 2, because 1 minus 1 is 0, 0 to the fourth is 0, plus 2 gives us 2. So we have the point 1, 2, and then when we plug in 2 for x to figure out what our function's equivalent to, 2 minus 1 gives us 1, to the fourth is still 1, negative 1 though, because that negative's out in front, plus 2 gives us a positive 1. So then we have the point 2, 1. Now remember, slope, change in y over change in x. And the order in which I use those points doesn't matter as long as I'm subtracting the same way. So if I take the y value of the last point and subtract the y value of my first point, I need to do that same order in my denominator for x, or vice versa. So what I'm going to do is start with 1 f of 1 and use that as x1, y1, and subtract 2 f of 2 as my x2, y2. So I'm going to have f of 1 minus f of 2 all over 1 minus 2. My y value and x value, then I'll subtract the corresponding y, x values and divide those. So this is going to be 2 minus 1 over 1 minus 2, which gives us 1 over negative 1, which is negative 1. Negative 1 is that average velocity between my time of 1 second and 2 seconds. So that speed would be 1 unit per second. But the average velocity is negative 1 unit per second. Now, the fun part is figuring out that instantaneous velocity. And we're finding the instantaneous velocity at the time of 2 seconds. So that's when x is equal to 2, we're going to find the slope of that tangent line. We know that the secant line between 1 and 2 had a slope of negative 1. So if you could see my point 1, 2 here and my point 2, 1, if I was to connect those to form a secant line, that slope is approximately negative 1. However, I want to know the slope when I have my tangent line at the point 2. So that's actually a steeper negative slope. Now this worksheet is just to get you familiar with the concept of the secant and tangent line. So what are we going to do? We're going to make a table and have our values get closer and closer to that point that we're trying to find the tangent line at. And that point in this case is that point 2, 1, when x is equal to 2. And the only method we know how to use currently is that tabular method. So let's go ahead. I already have this graphed and a table formed out. So let's go to that now and calculate that instantaneous velocity. And I kept this format the same as the other table, and I'll go ahead and share this link in the video description as well so you can play around with it. Except this time our a value is the point 2 in the x. So this point right here, 2, 1. Now remember, our secant line started when we used the x value of 1, which I'm using this slider to change that x value so that you can see that value getting closer and closer to the point 2. So here we have it. There's that secant line. That slope is indeed negative 1. When I use my x value of 1, I get negative 1 for my slope. If I was to move this in to, let's say, about 1.5, Well, we're getting closer to what the slope of the tangent line would be, but not quite there yet. So when I'm at 1.5 in the x, my f of x is 1.9375, which gives me a slope of negative 1.875. If I continue on to 1.75, you can see that's getting even closer to what the slope of the tangent line would be, and that slope is negative 2.73 roughly. If I want to get even closer, I'll go to an n value of, let's do 1.9, because 1.9 is even closer to 2 than 1.75 is. You can see that secant line is getting closer and closer to the slope of our tangent line. And then if I change this from 1.9 to 1.99, or 1.999, or so on, the changes become so small that you can't even see them visually. So if I look at my table, my next value when I did 1.99, I got a slope of roughly negative 3.94. And remember, I can't plug in 2 because I cannot divide by 0, and 2 minus 2 would give me 0. So if I did 1.999, that's negative 3.994. If I threw in another 9 in the next decimal place, that's negative 3.9994. We're getting closer and closer to what value? Closer and closer to negative 4 for our slope. So let's go back to the worksheet. And again, feel free to pause this video and play around with this graph, trying to find the slope of the tangent line at a different point. So change that a value and then make sure your n or your x values get closer and closer to your chosen a. But going back to the worksheet, so you could see as we got closer and closer to our x value of 2, our slope got closer and closer to negative 4. So our instantaneous velocity is negative 4 units per second, or that speed would be 4 units per second. And this was more of a physics application, but the concepts are the same as above. We're trying to find that slope of the tangent line, and we're going to use the slope of the secant line to help us out. So starting at an x value further away from the point where we want to find our tangent line at is not going to give us necessarily an accurate slope, but the closer and closer we get, the more and more accurate our answer becomes. So now this concept of taking the limit of a secant line as x approaches some value, that's all about finding that tangent line. And what we're going to learn later, and I'll go over more in depth when we get to that point, that tangent line of a point, that slope, is the derivative. But for now, we don't even know how to accurately find the slope without using a table, because we need limits in order to do so. So what we're going to do in the next few videos is go over a limit, and then we're going to go over how to solve that limit so we can get the exact value of the slope, which is going to help us for understanding derivatives. But for now, let's go ahead and dive into limits. And until the next video, good luck with your online learning.